In this video, we're going to talk about force diagrams. We're going to talk about how to find the magnitude, direction, and sense of a vector for a force. And we're going to talk about how do we break down those vectors into their components and add them up together into what we call a resultant vector. So let's kind of start at the beginning. Let's talk about free body diagrams, or sometimes we call them force diagrams. So what these represent are how are forces acting on certain objects. So we ignore all other interactions that are happening with our specific object, and we're just going to focus on the forces acting on that specific point. So think about me standing here. There's the force of gravity acting down on me. There's a normal force from the floor pushing up on me. So I can diagram the forces acting on me pretty easily. Now later on, we're going to talk about trusses and more complicated bodies like that, where there are forces that are acting in different directions, acting on different parts of your truss that will kind of interact differently. But when we're talking about a force, what we really mean is just an interaction between two objects. So an applied force would be me pushing on a chair. Gravitational force is an interaction between an object and the earth and its gravitational field. So really, we're just saying how are two objects interacting together to create a push or a pull. Now mathematically, when we describe forces, there are three things that we want to take into account. Number one is the magnitude of a vector. So if we look at a force vector, so imagine maybe there's an object that's sitting right here, and there is, I don't know, a string. So maybe a force of tension is pulling it up at an angle or something like that. The magnitude represents how big is that force vector. So if we were to kind of think about it in our drawing, I don't know, maybe it's something like this where it's kind of partitioned into three parts. So maybe this is 3 pounds of force, right? Our magnitude is showing how big something is. The second idea is the direction, and we're going to use an angle measurement to show what that represents. Now, most of the time, just to keep things consistent, we're going to use the x-axis as our basis for our measurement. So let's say we have our vector has a 37-degree angle with respect to our x-axis. So what we're going to say is we're going to call that the magnitude is 3 pounds. We're going to say the direction is 37 degrees counterclockwise from the positive x-axis. So notice when we're describing the direction of a vector, we're giving the angle measurement, we're giving kind of a direction of rotation, and we're giving a basis point. So again, 37 degrees counterclockwise from my positive x-axis. Now the third thing to describe vectors is what we call the sense, and this is going to help us break them down into force components. So the sense is kind of getting an idea of the direction of our vector in terms of left and right and up and down. So as I look at this vector, if I were pulling an object that way, there's a piece of my vector that is pulling left, and there's a piece of my vector that's also pulling up. So the sense of my vector would be rightward and upward. Maybe if I were to have a vector that looks something like this, my sense would be leftward and upward. So again, the three big things we need to take away from that is the magnitude represents the size of our vector, in this case a force. The direction is in reference to one of the axes, so 37 degrees counterclockwise from my positive x-axis. And the third thing we need is the sense. What are kind of the left and right and up and down pieces that we can break that vector down into? So now what we're going to do is we're going to use that idea to break down vectors to figure out if I have multiple forces acting on an object, how can I break them down and add them together so that I can see what that result would be overall. So let's frame our work with a little example. Let's say that we have a boat that's hanging out here and a couple of people are trying to pull the boat onto the shore. So we have their forces being shown as these vectors. So we've got vector A, we've got vector B. It looks like they're pulling with the same magnitude, but their directions and their sense are going to be different. So our goal is to figure out what is that total force. If we were to combine those two vectors together, what would that total force be on the boat itself? So let's talk about breaking that thing down into vector components. So first thing, let's just talk about how to describe the vector. We already mentioned before, we need magnitude, direction, and sense when talking about a vector. So in our case, the magnitude of our applied force is going to be 80 pounds. The direction is going to be 25 degrees clockwise from the positive x-axis. And my sense, it feels like, is going to be right and down. So we're going to use that idea, and we need to figure out how much of that applied force is pulling to the right, how much of that force is pulling down. So anytime you have an angled force, we need to break it down in terms of its x component and in terms of its y component. So we can use trig to solve that pretty easily. We know that we have our angle, we have our hypotenuse. So in order to find the x component or the horizontal component, we'd probably have to use cosine. To figure out the y component, we'd have to use sine. But there's also a little shortcut that we can use. So what I'm going to do is I'm going to describe this as FAX, which is the portion of the applied force that's in the x direction, and FAY is the portion of the applied force in the y direction. So let's talk about a handy little shortcut. If you feel good about the trig work, this is something that we can do just to save us a little bit of time. So if we're talking about FAX, again, we have the hypotenuse, we have the angle, we're looking for the adjacent side. We can use that to our advantage. And what we can do is we know, hey, FAX is our adjacent side. We can set that equal to our hypotenuse times our trig function. So instead of saying cosine theta equals FAX over FA, I'm just kind of skipping that step because I know that there is the hypotenuse portion of FA and the x portion is found by cosine in this case. So if we were to toss in our numbers, we know the magnitude of our applied force, we know our angle, so we have 72.5 pounds going to the right. That is our x portion of our applied force. And we can do the exact same thing for FAY because since it's the opposite side, we're going to be using sine to figure that out. So I could write it as FAY is our applied force times sine, plop in our numbers just like we did before, and we get a value of 33.8 pounds downward. Later on we'll talk about positives and negatives, but we're just going to keep it as rightward and downward for right now. So that's a handy little shortcut that we can use to solve portions of these vectors. But let's talk about our overall goal again, because what we're trying to do is figure out the overall force, adding all of our forces together to get one vector. So there's 3 steps that we're going to do in order to make that happen. Number 1 is we're going to break down those forces into x and y components, just like we did before. Number 2 is we're going to add all of our x components and all of our y components so that in number 3 we can use those totals to create a new vector. So let's go back to our example problem. We have these 2 individuals that are trying to drag a boat onto shore. So let's go to step number 1. Let's break those forces down into x and y components. We have our 75-pound magnitude. We have our direction. Now my sense is to the right and it's upward. So let's see if we can break that down. Let's just find FAX for right now. We'll put that in the back of our minds for the next step. So because I have my hypotenuse, FAX is my adjacent side. I know I'm going to have to use cosine to figure that out. And if I set it up, I know that the x portion of my applied force is hypotenuse times cosine 35 degrees, and that is going to the right. So I know I have an overall value for the x portion as 61.4 pounds. Now let's do the same for FAY, where since we're looking for the opposite side, we're going to use sine to solve for that. And if we isolate FAY, or if we use the shortcut that we learned just a little bit ago, we've got our 75-pound magnitude times sine of 35, and that sense is going up. So notice how all we're doing is we're just breaking those down into their components, and we're describing what direction those guys are moving in. Now let's do the same thing for the other person. We figured out kind of the rightwards and upwards. Let's figure out the rightwards and downwards one. So go ahead and pause the video real quick. Take some time and solve for the x component and solve for the y component. And then we'll move on to the next step together. All right, now I'm assuming that you actually paused it and you're not just blowing through this thing. But either way, if we try to figure out our rightward and our downward, we find the same magnitude for our x and our y, except for the y portion is going down instead of going up like we did in the last example. So let's move on to step number 2. We need to take those components and we need to figure out what is the overall x direction and the overall y direction. So how we're going to do that is we are going to kind of list those forces. We're going to organize them based on their direction and sense. And when I'm adding these together, anything that is going to the right and up, I'm going to consider a positive number. Anything that is going left and down, I'm going to show as a negative number. So let me show you what I mean by that. So we broke down both of our components to look something like this. And so I am describing my FBY for now as a negative number. So my FX, I have 61.4 pounds to the right for both of those. For my FY, I have 43 going up and 43 going down. So I need to add those together. Add my X's and then separately add my Y's. So let's do that real quick. In the X direction, if I add those two together, roughly we get 122.9 pounds, and that is going to the right because that's a positive number. If I'm going to sum my forces in the Y direction, 43 plus a negative 43, it comes out to be 0. So these are the coordinates for our brand spanking new vector. So let's move on to number 3. We've already found the magnitude. That overall force is 122.9 pounds. We found the direction because we don't have an angled force right there. So my new resultant force has an overall of 122.9 pounds because of those X forces that we added together. Now the Y forces kind of cancel each other out, so they gave us a nice, easy direction that we need to that we don't need to figure out. Excuse me. But we do know that our sense is to the right. So notice how we broke everything down. We added our X's together, we added our Y's together, and then we used that value to make a new vector. So that's nice and easy. It's really handy that the Y's canceled out, but what happens if we have an angle? How do we deal with that? How do we find direction for things that have an actual angle? So let's say that we have another example. Let's say I already went through step number 1 where I broke those forces down, and I found that I have an X component of the applied force as 22 pounds. The other one is negative 18. And in my Y direction, I have positive 14 and negative 12. So 14 going up, 12 going down. So let's do that same process real quick and kind of see what we come up with. So if we take the sum of all of our X forces, if I add those two together, 22 to the right, 18.536 going to the left, I have a net force in the X direction as 3.464. So that means it must be going to the right, because the positive X has just enough to counter the X component of B. And if we do the same thing for Y, 14 going up plus 12 going down, it means I have 2 pounds going to the right. So now we do have a Y component. So we've got to deal with that. So I have my X and I have my Y. What we need to do is we need to use them to create a brand spanking new vector. So I have my 3.464 going to the right. From the tip of that arrow, I'm going to continue going in the Y direction as 2 pounds, going up. And so our new resultant vector is going from the beginning of the first force that we drew to the end of the second force that we do. So this is the actual vector that we're looking for. So if our job is to figure out the magnitude and the direction, we already know the sense is right and up. we need to do a little bit of trig to figure out what that magnitude or what that hypotenuse is. So let's see what that might look like. In my triangle, it looks like, if I use this as my reference angle, it looks like we have the adjacent side and we have the opposite side. But if I'm looking for the magnitude, I don't even need to use trig. I'm going to pull out Pythagorean's theorem to figure that out. So I'm going to say 2 squared plus 3.464 squared equals my hypotenuse, or that overall magnitude, squared. So if I plop that into my calculator, roughly we get 4 plus 12. To isolate that hypotenuse, I'm going to take the square root on both sides, which means that my hypotenuse is 4 pounds. That is my overall magnitude. So we have our magnitude, we have our sense. Let's try to figure out what our direction is going to be. So again, I have my reference angle that I'm kind of looking for. I'm looking for my adjacent side. I'm looking for my opposite side. So I'm going to use tangent, TOA, opposite over adjacent. So I'm going to say tangent theta equals 2, which is my opposite side, over 3.464, which is my adjacent side. And I need to isolate for theta so I can get that angle. And the way we're going to do that is with inverse tangent. So if I take the inverse tangent on both sides, I have theta equals the inverse tangent of 2 over 3.464, which comes out to be a nice 30 degrees. So now I can answer my overall question that the magnitude that we found is 4 pounds. My direction is 30 degrees counterclockwise from the positive x-axis, and the sense of my vector is right and up.